I always say that the terms virtual network and software-defined network are redundant because all networks are virtual and software-defined. The only physical aspect of a network is the physical media and the interfaces. Everything else is virtual. What this means is that when you're designing a network, you're never designing just one network. You are designing multiple networks, or to put a finer point on it, layers of networks, okay? You can see where I'm going with this. In this clip, we're going to explore how the OSI layers are implemented both on individual devices as well as across the network. Now, check out these super simple topology diagrams. Yeah, I know this looks like something you create on your first day of CCNA class, but there's some really interesting design concepts hidden in here. Suppose that host A is running a secure shell or SSH client, and host B is running an SSH server, and host A wants to establish a session with host B. The SSH client on host A generates an application-specific packet, what the OSI folks generically call a protocol data unit, or PDU. In the Layer 7 PDU, you have purely SSH application data. This is going to include key exchange, authentication information, stuff like that. Remember how I said we roll up layers 5 and 6, session and presentation, into 7? This is an example. The SSH application handles those functions, and thus, for our purposes, we can just focus on the single Layer 7 PDU. So the SSH client passes this PDU to the operating system's TCP/IP stack, along with the destination IP address you see here, and a port number 22. The OS encapsulates the application PDU in a TCP packet that, of course, is marked with a destination port of 22 and an ephemeral source port. The OS then encapsulates that TCP packet in an IP packet with the destination address of 192.168.70.67, and the source address is going to be the IP address of a particular network interface. In this case, the source address is in a different subnet than the destination. Now, here's where it starts to get fun, as if it wasn't already fun. The OS goes through the typical routing process where it sees that the destination is in a different subnet, and so it knows it has to forward the packet to its default gateway. So the host sends an ARP request for the default gateway's IP, gets its MAC address, and then the OS passes the IP packet to the NIC driver along with the next hop router's destination MAC address. The NIC driver then encapsulates the IP packet inside of an Ethernet frame. So far, everything that has happened has been in software. It's all virtual. This encapsulation process is literally just appending more data onto existing data. That's all this is. But now we come to the physical layer, and here the NIC driver passes the Ethernet frame to the NIC itself. The NIC then appends an 8-byte preamble and encodes the whole thing as electrical impulses that it puts out onto the wire. This is called a Layer 1 PDU, or in this case, a Layer 1 Ethernet packet. Yes, I said a Layer 1 Ethernet packet. All right, I told you that this was going to get a little strange. Okay, so that's how network layering works on an individual host. And believe it or not, that was the easy part. We're going to get a little bit more complicated here. All right, look at this diagram. This is a layered representation of the whole network. On the left, we see host A's layers, and we've walked down through those all the way to the physical layer. When host A's Layer 1 PDU, that Ethernet packet, gets to switch A is going to decapsulate the Layer 2 Ethernet frame. Because switch A is just doing bridging, it's not doing any IP routing, it is only going to pass that Layer 2 Ethernet frame along to router A without modifying the frame's payload. Once router A receives that frame, it is going to decapsulate the IP packet from the Ethernet frame, process it, decrement the TTL, encapsulate the IP packet in a PPP frame, and send it along its point-to-point link to router B. Now, I'm not going to walk through the rest of the process because you already know how all this works. But notice how we have our application data zigzagging up and down these layers as it moves along the network. This is a really simple and small network, and yet the SSH traffic jumps between layers about 24 times on a one-way trip. And people wonder why network troubleshooting takes so long. Now check this out. Look at the network layer on host A. If you draw a horizontal line to the right, you will run smack into router A. Host A and router A communicate via IP at layer 3, and they do so by encapsulating those IP packets inside Ethernet frames. You can do the same thing with router B. Draw a line to the left and you hit router A. So routers A and B are connected at layer 3. And you can do this with any layer. At the transport layer, draw a line from host A and you'll hit host B. Now, by the way, do you remember another name for the transport layer? It's called the host-to-host layer. The TCP processes running on host A and host B communicate via layer 4, the transport layer, by encapsulating those TCP segments in IP packets. Remember the Bob Metcalfe quote, networking is inter-process communication. How many processes are communicating here? It's not just one application operating at layer 7. We've also got TCP, IP, Ethernet, or more specifically MAC. These are protocols communicating all at different layers. Why do we have all these layers? Well, each layer performs specific functions that collectively contribute to the goal of internetworking. Again, inter-process communication. Layer 1, the physical layer, encodes bits as electromagnetic energy and sends them out over some medium, like twisted pair cable. The NIC is a layer 1 device, and gigabit Ethernet is an example of a physical layer protocol. Layer 2, the data link layer, handles data transfer between two nodes that are connected to a shared medium. Now this sounds a lot like the physical layer, doesn't it? Well, in the early days of Ethernet, systems were connected to a shared physical medium. It was actually a big yellow cable. MAC addresses were invented so that those devices could identify each other. Otherwise, one device would send data and the other devices would have no idea where the data was coming from or who it was intended for. That's why they called this Ethernet. It was just like data floating around in the ether. So MAC addresses were originally meant to function as identifiers. But today, switches, and more specifically VLANs, have replaced that shared medium. In essence, the VLAN, also known as the broadcast domain, also known as the subnet, is the shared medium now. So think of two routers connected to the same VLAN. The routers are not physically connected to each other, but they are in the same VLAN. And there may be several other routers in the VLAN as well. Ethernet still uses MAC addresses to uniquely identify network interfaces. Of course, there are other layer 2 protocols such as PPP and HDLC, and they fulfill that same goal of enabling data transfer between two nodes connected to a shared medium. Network layer, layer 3. The network layer handles data transfer between any two nodes, whether or not they're in the same subnet. So think back to our example with host A and host B. They're in different subnets, so they cannot communicate at layer 2. They have to communicate using IP. One thing I want to point out here is that IP addresses do not address hosts. They actually address interfaces, just like MAC addresses do. Why do we need two different addresses for the same interface? We don't. This is actually a big mistake that was made back in the early days of IP. Some folks decided that IP should name an interface rather than the node itself. This is actually one reason IP mobility is so difficult today. All right, one more layer, layer 4. The transport or host-to-host layer is a bit different than the first three. Layers 1 through 3 are concerned with moving data between endpoints. But remember, yes, I'm going to say it again, networking is inter-process communication. Just moving data from one network interface to another is not enough. A process on one endpoint needs a way to indicate which process it wants to communicate with on the other endpoint. This is where layer 4 comes in. Going back to our example, how does an SSH client indicate that it wants to connect to an SSH server as opposed to a telnet or a web server? It specifies a transport layer address, more commonly known as a port number. An SSH server normally listens on TCP port 22, TCP being the transport layer protocol, port 22 being the transport layer address.